As a laboratory in space, ISS provides a place to investigate how things work when there's no gravity, a necessary step on the road to humankind's future exploration of space beyond low Earth orbit. The Capillary Flow Experiment is a physical science experiment that's been underway on board the station for a few years now, since Expedition 9. This morning, we're going to learn about that work. Joining me now from Portland State University in Portland, Oregon, is Andrew Wollman, a research assistant on the Capillary Flow Experiment team. Good morning, Drew.
Good morning, Amiko. Glad to talk with you.
We're happy to have you here. So, the name of the experiment indicates you're looking at capillary flow. What is capillary flow, or the capillary force?
Capillary flows refer to fluid flow that's powered by a capillary pressure, and that pressure comes from three different things. First is surface tension, which is a fluid property that wants to keep the fluid together. Second is the wetting condition, which is best described or illustrated by dropping a raindrop on a windshield and watching it beat up, or putting some oil in a hot pan and watching it spread out. And the third thing is the shape or the geometry of the container itself. So those three things can create a pressure in the fluid that spontaneously pump it without a moving part.
Can you explain to me, in the context of future space exploration, why is it important to know how these fluids flow in the absence of gravity, and how those flows can be controlled in the absence of gravity?
Okay, so capillary flows are normally dominated here on Earth by gravity, and so we don't notice them. But when you go up into orbit, these flows are all over the place, and we like to study them. For example, bubbles in your soda on Earth will rise to the top and come out. But bubbles in space stay suspended in the fluid, and they cause problems with some of the equipment. Also, we would like to move fluids around without having a pump or a moving part, and so we can do that by changing the geometry of the piping.
Okay, and so what are the benefits of this information that we are getting from this study?
Well, the largest benefit that we're getting is high reliability. So most of the fluid management systems on board station today have been designed without knowledge of how capillary forces behave in orbit. And so there's problems. And so we want to mitigate these problems by putting into place some of the things that we've learned.
Can't you use computers to simulate how those fluids behave in space?
Yeah, we can use computers to simulate the flows, but they're just that. They're simulations or models. To help verify our simulations and our models, we need to have actual experiments and view what's actually happening so that we get a higher fidelity solution.
Okay, well, I know that ISS and the microgravity environment is very essential to not only this experiment but many experiments, and so it is a perfect place to conduct this type of experiment. I know the experiment is investigating fluid flows within containers of different shapes. Can you tell me about some of the different tests that you use to gather the data on how the liquids are behaving in weightlessness?
So depending on the test cell, we have 15 different test cells up there right now, and each one is a unique shape for a solution to a math problem. And the astronaut will pump the fluid into the test chamber, and we'll watch the fluid migrate from one end of the chamber to the next, all on its own, or we can drain the container and watch how the draining process is affected by the shape of the container. We also can produce some bubbles on purpose and put those bubbly froth inside the test chamber, and then we can study how we can separate the bubbles from the liquid.
So how do the astronauts on the station, how are they participating in this capillary flow experiment? What are they doing?
Yeah, the astronauts are essential. They are our lab partners up in orbit. So the astronaut actually is the individual that's turning the knobs, opening the valves, pushing the plungers. It's very interactive. And us here on the ground are communicating with the astronaut in a control center, talking to them, telling them, okay, we'd like to open valve 1, see what happens. So in addition to just following the crew procedures, the astronauts also have a unique perspective, and so they're able to tell us things that are happening that we may not necessarily be able to see from our downlinked video.
I know that, as I mentioned before, this experiment, the Capillary Flow Experiment, has been gathering data for a few years now, as I mentioned earlier, since Expedition 9. Can you tell us what you've learned so far, and then what's the next step in this process?
Yeah, we've learned quite a bit, and most of it is pretty boring. It's all math. Most of it is math, but that's important for design tools for engineers here on Earth to better improve their designs for future spaceflight. As a result of the CFE experiments, we've been able to publish more than 20 papers. We have 6 terrestrial applications come out of it. We've had 3 patents, including an astronaut coffee cup, which we are hoping to put on board station on SpaceX 6.
It's even got a handle. And as you mentioned, some of the results are math, and I would just say I wouldn't qualify it as boring necessarily to a lot of folks, and including yourself. It seems that you really seem to enjoy the work that you're doing.
Oh, absolutely, yeah. Math is super exciting for our group. We really get off on it. It's super exciting.
That's great. Well, I really appreciate your taking the time to talk with me today about that experiment, and best of luck on the continuation of your studies. Thank you very much.
Thank you.